So thank you so much for the invite. Really happy to get a talk at this event. Met a bunch of new people that I really, really like. And I get that it's Thursday, a couple of sessions before lunch. So I'm going to start off with something that's very new for me and will be very new for one of you. I want to volunteer somebody to play a game. And if nobody volunteers, I'm going to pick a new friend that I've met here at the conference. Going once. Oh, yeah, please come up. Round of applause, please. The game's super simple. It's just like a kind of like Pac-Man style-ish game. You have this mouse here and you've got to find the cheese. And basically everybody in the crowd, you're just going to be looking for the rule that makes the mouse successful at grabbing the cheese. So you can just use these up, down, side to side here. And if anybody has any tactics that they want us to explore, just shout them out.
Up. Go up.
Oh, yes, yep, that's good. Yeah, so you get 10 attempts, so you can go fast, take your time on some. And if you think you've figured out the rule, keep it to yourself for the moment, and you can tell me.
Hmm? It's a trap.
Yeah, you got trapped that time. Yeah, you lost. Okay, any other tactics? Anything anybody wants to? Okay, there we go. Nice work.
I see.
Try the same thing again.
Avoid the corners.
Ups.
Oh. Okay.
Damn, we're not very good at this, huh?
Well, it's not a professional.
Okay. Thank you so much. That was. So anybody have any ideas for what the rule there is?
Thought I did, but
What were you thinking?
it looked like when he went to the corners,
Uh-huh.
it said trapped. I don't quite know what trapped
Uh-huh.
but then there were other things that said trapped. So
Yeah. So we have a room filled with people that study first passage time theory, and the actual rule, slight delay, is that you've got to take longer than 4 seconds to get to the. Sorry. You're going to take longer than 4 seconds to get to the cheese. And I think this is more representative of a much kind of wider phenomenon that often time, so when we're asked to come up with a causal mechanism, time is often not considered as an important causal variable. And, this is independent of whether we study first passage times for a living. Can't believe none of you got it. It's crazy. Time conditioned processes, or time-dependent solutions to master equations. And this is part of like a general cognitive bias that we have. So if you're a biologist and you see a kind of you have a fluorescent protein in a population of cells, you'd be very likely to come up with time-independent mechanisms describing, say, the ability of cells in that population to express a given fluorescent protein or to not. So if you have a bimodality like you have here, you'd be thinking of steady state mechanisms. But there are many other things, many other reasons that we don't think about time. Time's often a frustration. So if you're thinking about modeling a deterministic system, if time's important, then fixed points are no longer enough. You have to do full time-dependent solutions. If you're in a stochastic setting, and say you do generating function approach, like classic kind of like turn the crank, nice ODEs in steady state approximations end up becoming intractable PDEs very often under time-dependent formulations. And even experimentally, right, time is both, it's time expensive and resource expensive. And so I think it's important that we understand the circumstances in biology when time is the origin of qualitative behaviors, especially in paradigms when time is considered to be a nuisance. I've been there, getting rid of time without really like a good explanation behind it, because it allows me to solve an equation. And in general, this talk is going to be concerned with the novel qualitative phenomena that can occur when stochasticity and time dependence interact in unexpected ways. This is building on, some other themes in the talk, in the workshop. This is not a diffusion-based talk, okay? I love the diffusion talks. This is not one of them. Eric the other day mentioned something about understanding the functional capacities of noise. That's very much kind of the spirit of this talk. Builds on themes that Trevor's mentioned, these noise-induced patterns, and I presume stuff that Jay's going to be talking about tomorrow. And it's also related to some work that Ethan's done in the past year, which I've really liked. And the talk's going to be split into like two main parts. The first is kind of centered around something I published earlier this year. And the second is something that's a work in progress, including this very cheeky photo of Anj Kumar, who was apparently collaborating with everybody in this workshop. Yeah. So there's just a couple of definitions that I want to introduce. So the first is like, what is a mode of probability? So if we're in kind of a population level biological setting, so the example that I'm going to be using throughout the talk is fluorescent proteins and populations of cells. So just please get used to it. Essentially, if you have a population of cells and you say you do a histogram over the fluorescence of all of those cells, if you find peaks in that distribution, that is a mode of probability. It's a signifier of a subpopulation within your overall population of cells. A mode of behavior, on the other hand, is something that while if you have, say, two modes of behavior, you might see this reflected in the population level, is also something that's available essentially to be switched into on the level of an individual cell in that population. So sometimes these two things nicely coincide, sometimes they don't. So there's standard like paradigms of biological bimodality that I think many of us will be familiar with. So often in like biological steady states, constant environments, no kind of like external noise, external perturbations, and where you have like concentration homeostasis of gene products. But the type of bimodality that I'm going to be interested in today is called transient bimodality. And it arises from a delicate combination of initial conditions of a stochastic process, relaxation rates, and the eventual steady state that's going to be achieved. And so just quickly, what is transient bimodality? It's a situation in which you start off with a process that has one mode, transiently becomes two modes, and returns to one mode. So just for those that are more pictorially inclined, start off with something like this at some early time. At some middle time, you get two modes in your distribution, and at late times, you go back to a single mode again. This is the kind of extreme or rare event that I'm interested in my talk. But even though it may be extreme or rare compared to other processes, they can exist for long, like intermediate times. And it's not just something that you can see nicely in the theoretical model. There's kind of many parts of biology and even beyond biology where transient bimodality is like a kind of well-known phenomenon. And so there's work done in the 2000s, classic work coming out of James Collinson's lab, kind of showing transiently bimodal distributions of fluorescence in the GAL system. There's even earlier work where you get like a really nice, clear identification of these like two modes appearing in transient times. More recent work, I suppose it's not really that recent anymore, but in the kind of mid 2010s, work coming out of Richard Murray's lab took a more single trajectory approach to this using cell flow cytometry, and there's been some even more detailed experiments showing transient bimodal trajectories also in the GAL system. And so what are the different mechanisms that can give rise to transient bimodality? So first type of mechanism that you might think of would be like kind of deterministic. So this is like a very popular approach that was used kind of in the early days of systems biology, where if you were to spot something like this, you have two subpopulations in your overall population, you might be wanting to look for models that give rise to deterministic bistability. And so in this case, it was a particular kind of part of the lactose utilization system that the lab of Alexander van Oudenaarde was looking at. Their model predicted for one of the proteins involved in the system that you get essentially predicted by stability, which in some cases really nicely overlaps with the stochastic formulation of their same model. So essentially you have the modes kind of that are identified with an actual mode of stability there. And generally speaking, bistability does imply this connection between the individual level and the population level. So your modes that you see on the kind of population level, your subpopulations, often correspond to the types of behaviors that are available to individuals in that population to be switched between. And where deterministic mean values coincide with probability modes, stochastic modes of behavior are actually really nice and easy to define. We can use these properties of the deterministic systems to start talking about what a mode of behavior might be within a single cell just by looking at a snapshot of the population at a fixed time. But this is not always true, and there are many cases in which deterministic and stochastic models, even with the same mechanisms, break down. Joel Kaiser's name's been brought up a couple of times already, and of my favorite stuff that he, I suppose, helped lead the path towards is his Kaiser's paradox, which is essentially a statement that the qualitative features of deterministic and stochastic models very often do not agree. So it's not just a quantitative statement. It's saying that, say in this case, we can have regimes of Alexander van Oudenaarden's model where you do not have stochastic bimodality, but you do have deterministic bistability. In Kaiser's case, he was looking at a reaction scheme where stochastically there was an absorbing state, where all of the probability mass kind of went out of the system. But if you modeled it deterministically, you would always get a kind of finite valued fixed point. There are many systems that kind of express this type of behavior. So, for example, if you just have a kind of simple genetic autoregulation motif, this will always be deterministically monostable in the absence of cooperativity of the protein binding to the gene. But there are large swathes of parameter space that admit stochastic bimodality. And this is just an indicator that to say for problems where stochasticity is a dominant force, deterministic prescriptions typically cannot be trusted. And so this connection provided on the deterministic level between a mode of behavior and a mode of probability is something that becomes more complicated when we can no longer trust those types of prescriptions. So what can be said about the relationship between a probability mode as defined from a population snapshot and the modes of behavior that are available to individuals in that population? So in some cases, the two definitions do overlap, and in very common paradigms that I think many of us are kind of used to. So in cases where discrete molecule number effects are unimportant, in steady state regimes and where you have Fokker-Planck dynamics. So you can go into any kind of classic stochastic dynamics textbook and see this description of Fokker-Planck. This is from Van Kampen's book. Fokker-Planck equation, you have a potential, the potential has two wells, and there's kind of nice simple calculations showing that if you have this type of setup, the time to switch between the two wells is exponential in the height of the bar, yada yada. And so what you get on the between the single cell level and the population level actually corresponds quite nicely. But in transient bimodality, this is not necessarily the case. There are ways of breaking down this connection between the single cell level and the population level where you can get two modes of probability, but with really only one mode of behavior. And a really simple example that I love to use for this is actually just very simple kind of Michaelis-Menten enzyme kinetics. And so in what I'm going to show you, it's important that you think of the substrate as a green fluorescing molecule that is getting slowly consumed by an enzyme. See it getting consumed. Because it's a single mechanism of decay, you might think that the kind of transient probability distribution, if you have a bunch of these processes in tandem, would always be monomodal. But this is not necessarily the case. And so just in what I'm going to show you, essentially an evolving probability distribution of trajectories taken from this process and a hypothetical population of cells that I simulated corresponding to what's going on here. And so in this example, you start off, everything's like super dark, but it's highly fluorescing. I know that seems kind of counterintuitive, but essentially as the substrate starts decaying, you start seeing a little bit laggy, but you start seeing the colors changing. And at a certain point in time, you get the second mode appearing, which is essentially the origin of this depends on the initial condition, depends on the relaxation kinetics, and the position of the final state, in this case, which is an absorbing state. There's no requirement that for transient bimodality you have to have an absorbing state. This is just one of the simplest examples that you can have. There are kind of more informative ways of looking at this. So I can put side by side this level of individual trajectories that tell us about the number of modes of behavior that are available, and have this against the kind of evolving probability distribution on the right-hand side. And we can see that on the level of trajectories, there's kind of just noise about this mean. Although on the population level, you get kind of very long intermediate times of having this bimodality. And this corresponds to a breakdown of the kind of classic assumptions of saying that if you see two modes of behavior on your population level, that you would expect to have these kind of two switching modes in your population. Now, it did take a while of searching through the literature on these types of problems to find stuff that had been done before. But there was actually a decent amount of literature in the 80s and 90s that was focused on this behavior. So Prigozhin and Nicholas identified this. They called it a bifurcation behavior in time. It's been widely observed in a range of systems. I was telling Sid about this the other day, and to quote Sid, he was like, "Yeah, I'm not sure about Prigozhin. From what I heard, he seemed like he could have been a first-class asshole." I can't verify that, but I do like his work. And there is, and they point to it, there is like utility to having transient bimodality. So in some ways, it's kind of a cheap mechanism to generate bimodal subpopulations in ways that don't necessarily encode that ability to generate subpopulations in the control mechanisms of a single cell. So once you've achieved your kind of final state, there's not going to be a way that you'd reactivate those developmental pathways, say, and end up with cancer-causing mechanisms. It has a purely time-dependent origin, which indicates that the behaviors driving cell differentiation are not going to be active once homeostasis have been achieved. And it can also happen in parallel with changes in the environment as the system is kind of thrown out of equilibrium, which I think is kind of cool. And it does have a transient bimodality itself, long and transient history. So beyond the work of Prigozhin and Nicholas, there's a lot of work coming out of the Brussels School of Statistical Physics, kind of focused on this work. So a lot of terms come up here: adiabatic explosions, stochastic resonance, and transient bimodality, thermal explosions, yada yada. This was typically referred to as explosive behavior at the time because of that appearance of the second mode, kind of very suddenly kind of at odds with the rest of the population. And transient bimodality can have many different origins. I wrote about this in something that came out earlier this year. Everything I've been showing you so far is really focused on this intrinsic noise-driven version of transient bimodality. I think, like I said, I think Ethan's been doing some work as well that's kind of more centered around this, like more environmental or extrinsically noise-driven versions of this type of phenomenon, which I also think is very cool. Okay, the transient has passed, hopefully. But if we want to understand the origins of this noise-driven transient bimodality, one of the simplest cases that we can look at is just a simple Markov chain where we can change how kind of slow to fast or fast to slow the evolution happens across the chain. So it's just parameterized by this one parameter alpha. If alpha is less than 0, so says some of the previous literature, you're accelerating along chain. So you start from slow and end very fast. This was widely reported to be something that you needed in order to get transiently bimodal mechanisms. So here's an example from this model where we have alpha is 1. So this would just be like molecules decaying proportional to their number. And you just get this nicely evolving monomodal transient. But there are many cases of this kind of regime where if you take alpha less than 0, so say alpha less than 1 here, you get very kind of large regimes of strong transient bimodality. And you could think of mechanisms of antibiotic stress kind of corresponding to this type of mechanism, where you have initially kind of very slow development, then followed by kind of like fast responses after that. Now, to understand the intuition behind this alpha less than 0 causing the transient bimodality, there's like a little schematic that I drew up. So just for sanity's sake, we're going to start off on the right-hand side and go down to the left. So x naught here is just a continuous version of n. And the acceleration increases along the chain. So you could think of like individual stochastic trajectories like occurring along this axis. And this kind of nice mode here that we centered around some mean value. But any outliers here are going to accelerate away to the end incredibly fast, right? The outliers race away towards the end, creating a second mode. As this process evolves in time, the modes, the kind of trailing mode shifts, and the second mode gains mass until it will gain eventually all of the mass. So that's the kind of intuition behind some of these mechanisms. But this is not the only transiently bimodal regime, and this is why I've actually been having a lot of fun resurrecting this literature from its death in the early 2000s. So as I showed before, we get transient bimodality in this nice enzyme kinetic scheme. This has no regime in which you're constantly accelerating as you go along the chain. And you end up with situations like this, where you get strongly bimodal situations at transient times, even though you don't have this accelerating property. And so we wanted to try and get an understanding, a mechanistic understanding of what's going on here. And so one thing that is kind of important if you're investigating bimodality is that you actually have measures to quantify how strong bimodality is. One way of doing that is just looking at the height of the modes. There's many ways of quantifying bimodality, but some of them are less useful than others. And essentially, by taking the heights of the modes, the heights of the valleys, we can actually construct a nice metric here that if the two modes are the same height and the valley is 0, the value is 1. If one of the modes becomes the same height as the valley, then the value is 0, and it's always defined as 0 if you're in a unimodal regime. And what we found is that we took basically this Markov chain model here, and we found the maximum value of this bimodality coefficient along any given transient. And there's actually a very nice phase transition in this value of alpha at about alpha is about like 0.6, which we found really puzzling for quite a long time. But importantly, it points to this kind of new regime of transiently bimodal behavior that has not been previously explained. And we can also show that stronger bimodality occurs for shorter time periods. It's like an intrinsic trade-off. So essentially, we can look at, say, the two parameters essentially that make up this model, the length of the chain and this parameter value alpha. If as alpha gets more negative here, the maximum value of bimodality coefficient that you would predict gets larger, as it does if you increase the length along the chain. But if instead you're looking at the fraction of time that you get reasonable levels of bimodality as the transient evolves, there's actually a big trade-off in that the longer the chain is, the shorter the fraction of time that you're exhibiting bimodality. So there's like kind of nice intermediate regimes here where you don't want super low particle numbers, but you also don't want it to be too high if you wanted to see this phenomenon at all. Now, we've been looking for like more theoretical predictions as to why this occurs. You can actually see the occurrence of this phase transition, divergence in the Fana factor, the mean field limit. So to show this, you can. It's important to calculate the acceleration along the chain. You can do the simple calculation, you get something like this, and this in itself is pointing that for alpha greater than 0.5, so which is like kind of close to 0.6. We're still working on that deviation, but for alpha greater than 0.5, there is a deterministic force that for large values of x essentially is pushing you away from the barrier. When alpha is less than or equal to 0.5, this force decreases massively. This actually translates into a divergence in the Fana factor. You can show the Fana factor is essentially proportional to this acceleration, and essentially in the regime where alpha is less than a half, as you go towards the absorbing boundary, you would get this really nice kind of divergence predicted in the Fanon factor, which is obviously unphysical. I'm almost done. The last thing is that essentially first passage times actually show why, as we do first passage time analysis, you can show why there's a decreasing relevance of transient bimodality for large n. So by first passage time, I just mean from starting from x0, you're interested in the probability distribution of times that you're going to end up at the origin. Because this is a multi-step Markov process with distinct rates, it's just a hyper-exponential distribution. If you look at the shapes of these distributions, you can show that the regimes where you get the transiently bimodal behavior actually have these like very symmetric first passage time distributions. And if you take some approximations here, you can show that the coefficient of variation of the first passage time distribution actually has a noise that decreases largely in time as system size increases when you're in the regime of alpha less than or equal to a half. And this is essentially the reason underlying why transient bimodality is much less prevalent as you get to large system sizes, because there is just not going to be a long fraction of time over which the noise is great enough for that phenomenon to occur. There's some quick takeaways. So the combination of stochasticity and time dependence can promote novel qualitative system behaviors. Transient biological processes can generate distinct behavioral modes without agents exhibiting these two different modes of behavior. And intrinsic noise-driven bimodality arises from a combination of this reaction acceleration, giving rise to this divergence in the Fanon factor, and outliers inherent to the kind of noise in that process. So this was work done alongside Augustina Soukis and Khan Ojal, both at the University of Melbourne. Ange, over there, colleague of mine at SFI. And I just wanted to kind of emphasize one spin-off of this work. So I was telling Jay about this work at NITMB last year, and we ended up talking about the kind of issue of actually quantifying bimodality in the first place. Not a very easy thing to do. Jay has a fantastic student, Dongju Lim, who essentially took a whole range of these different measures of bimodality, and we trained a machine learning program essentially that takes into account many different aspects of what quantify a bimodal distribution and lead to very good predictions that have been useful in identifying bimodality in omics data and stuff like that. Yeah, thank you very much. Really good workshop.
Time for a couple of questions. Yeah.
Okay, I got a lot of questions actually.
Just one, Alan.
Right, my PD brain, my pattern information PD brain, first thought was like metastability. I've like Alan Cam will give you transient bimodality.
Mm-hmm.
How do you interpret that in your framework? Just like one of the simplest models of phase separation, Alan. Transient bimodality. So it's really quite a generic phenomena, even simplest models.
It's generic. I think, I mean, I do want to, okay, if you have like a kind of suite of these different models that exhibit the phenomenon, we should spend a bit of time talking afterwards. I think why I was so interested in it originally is that it often is quite a rare thing to find. So if you're like playing around in models of like chemical kinetics, like it's a very rare to find that transient bimodality that is distinguished from steady state mechanisms of generating that bimodality. So, and I suppose the other thing is that it may be that these mechanisms can generate the phenomenon, but I am interested in the kind of physical reasons as to why it occurs. What are the kind of special conditions on the noise of the process combined with those relaxation rates that are actually going to give some intuitive understanding of the phenomenon. But I mean, there's a lot of work still to be done. Obviously, what I showed here is an explanation, is a case study, right? It's not full proof. So, yeah, would like to talk more.
Yeah, I mean, if you're looking for maybe something structural to define this in stochastic process, it sounds like a spectral gap.
Mm-hmm.
You look at the spectrum and any kind of spectral gap is what you're looking at.
Yeah, I think it just depends on the eigenfunctions as well, though. I think you can definitely get a lot of understanding from, doing looking at the eigenfunctions and the eigenvalues. But in general, I found it. It's not that I haven't looked at them. I have. I just found it really hard to tell a cohesive, consistent story there. But there probably is something deeper. I know somebody, I think it was Ethan the other day, was mentioning Fouquet theory and the potential applications here as well, which kind of like very similar idea, right? But yeah, you have ideas. Come to me.
Yeah, you look at in any of these systems, the first couple of eigenfunctions probably look like the two peaks, and then you're just emptying one into the other.
Well, so obviously the first eigenfunction is definitely the it's the stationary distribution or the absorbing state or whatever you have. But the second isn't, because often so it might be showing you what the kind of trailing distribution looks like as it kind of settles in its final place. But often the transient bimodality can start happening long before it actually gets to that final point. So the other eigenfunctions do become important at times of interest. Yeah.
Hold on.
Oh, sorry.
Yep.
Not question, just a short comment. Yeah, I found it a bit surprising the way how you presented time in biology at the very beginning. I mean, any life system is not out of equilibrium system, so it's time dependent by definition. We are all aging, right? So in that sense, I think the time biology cannot be without time. So in that sense, it was a bit confusing from.
No, I love you. That's a great comment. No, absolutely. Like all of biology is transient, but a lot of I don't know, from my experience, like learning how to do biological modeling and my experience observing how other people do, a lot of the time people don't take that as seriously as we might hope. I'm glad that you do.
Wait, one more question. Yeah, go ahead.
So in physics, there's this concept of dynamic stability, right? If you have an incline with a marble, you can just keep doing this, and it'll sit there, right? And likewise, there's a cousin concept of dynamic bistability, which is like you have a potential well, and the marble is sitting here, and if you move it very slowly, okay, it's monomodal, right? It's there, just moving with the thing. But if you move it fastly, if you move it faster than the relaxation rate of the marble, having something do this turns out to be equivalent to having a double well. And then you get dynamic bistability. You can get dynamic hysteresis. Like that, there's a huge literature in physics of magnetic materials and so on that you might want to look into.
Yeah, I'd love to see that. I mean, some of the best examples that I've actually been comparing to have been primarily from physics. Like
so in analogy to your system, which just decays to zero in an accelerating fashion, you can imagine that you just flip it back now, right? And it now goes back. And if you keep doing this, you'll get like a seemingly stable double well system, kind of.
Okay, that's really fun. Okay, yeah, you'll have to show me.
Right, let's thank James.
Thank you.